Okay, so having proof that the algorithm actually works, let us now try to analyze it. To analyze the algorithm, we can compute the number of steps that it executes, exactly as we saw in the first example. So we're going to form a table again of the cost and times, and for each statement in the algorithm, we try to find what is the cost. Usually the costs are constants, because normally it's basic operations that are being carried out, and each of those basic operations take a constant time. So by the time, even if it is more than one operation, by the time you add constants, you're going to get another constant. So each statement is constant. What is important is how many times are we going to execute it. Alright, so let us start from the for loop here. As I told you in the first example, to know how many times the heading of a loop will execute, try to find how many times the body will execute. How many times the body will execute. If you can find that, then you just need to add 1 to the number of times that the heading of the loop will execute. Now this loop runs from 2 until n. Okay, a.length is actually n. Remember we said n is reserved for the size of the problem. And so we're going to assume it is n. A.length is actually the n. So if the loop runs from 2 to a.length, it means actually it will run n minus 1 times. Yani the body of the loop will run n minus 1 times. And as we know, there will be always one more check-in that will allow us to exit from the loop. Okay, the last value of j, remember, is n plus 1. So at that time, you will see that j is not within 2 to a.length, and therefore the loop will stop. Okay, so basically this loop heading will execute n times. So that's what we put here. Okay, it costs C1, constant C1, but the number of times it will execute is n. The second statement is a simple assignment, similar to what we saw in the first example. So the cost is constant. We're going to call it C2, and clearly it's going to execute the same as the number of times the body of this loop will execute, which is n minus 1. So we will have C2 n minus 1. The next statement is a comment. We don't normally count comments, so you can ignore this completely if you like, or if you wish, as the book did, you can say the cost is 0. Okay, it will execute n minus 1 times, same as the number of times the body will execute, but because the cost is 0, eventually this will be 0 anyway. Alright, next we have this initialization of I becomes j minus 1. So again, it's just a simple assignment and subtraction, so both of them, if you add, will be a constant, and this will execute the same as the body of the for loop, which is n minus 1. So we have C4 n minus 1. What about the inner loop? The inner loop says while I is greater than 0 and a at I is greater than key, go inside the loop and basically shift AI to the right and decrement I and go back. In other words, we are trying to find the correct place to insert AI. Now, as we saw in that example where we show the steps of the insertion sort algorithm, the number of times this inner loop executes depends on the arrangement of the elements in the array. It's not fixed, yani. And therefore, the best we can do is to use a variable to denote the number of times. So what we will do here is, since we know that the outer loop will execute for j equal to 2, 3, 4, 5, and so on until n, where n is equal to a dot length, we are going to say that this heading of the outer loop will execute some variable number of times. And this variable, its value actually changes with the j. And therefore, we're going to call it tj. Okay, so t2 when j is equal to 2. Okay, we will say, let's say this loop, the heading of this loop will execute a variable t2 times. Okay, 2 here is just an index, it's not indicating any value. Okay, it's just because we have many different values for each value of j. That's why we're gonna give them different names. If you wish, you can call them A, B, C, D, and so on. But since actually the number depends on j, it is a good idea to tag them along with the j. Now, if the heading will execute t2 times, how many times the body will execute? Obviously, the number of times the body executes, the heading execute, minus 1. So the body will execute t2 minus 1 times. Okay, if you come back again with j equal to 3, how many times will this heading of the inner loop execute? We don't know. So we call it a variable, but this time we'll call it t3. A variable to t3. And the body of the inner loop will execute at that time t3 minus 1. Okay, and so on. So for 5, for example, we will assume the heading of the inner loop will execute t5 times, and the body will execute t5 minus 1. So the question now is, in total, throughout the iteration of the outer loop, how many times will we execute the heading of this inner loop? In other words, this statement number 5, how many times are we going to execute it? Clearly, we just need to add these t's. Okay, just add them up until tn, and you will get the total number of times that this will execute. Therefore, we're going to represent this simply as summation of tj for j from 2 until n. The last value you can see is n. So summation of these tj's will be the number of times the heading of this loop will execute. Similarly, each of these two statements inside the inner loop, statement number 6 and number 7, again, to find how many times they will execute, just add this t2 minus 1, t3 minus 1, and so on until tn minus 1. In other words, it's going to be a summation of tj minus 1, okay, for j from 2 until n. This is the cost of each of these two statements. All right, and therefore in our table here, this is what we put, that this statement will cost a constant time, call it c5, but it will execute tj, summation of tj for j from 2 to n. All right, the statement number 6 is similar. The only difference is, instead of saying tj, we have to subtract 1, because again, remember, the body will always execute 1 less than the heading of the loop. T7 will execute in the same manner, the same number of times like statement number 6. Okay, so but we're going to use two different constants for the 2. The last line is a simple assignment. Okay, it will simply execute the same number of times the body of the outer loop will execute, which is n minus 1. So we have C8, and the number of times is n minus 1. So this is basically the number of times each of these statements will execute, and all we have to do now is to add them up to find the running time of the whole algorithm. And therefore Tn is going to be C1 times n plus C2 times n minus 1. We can ignore this because this is going to be 0. So just go direct to C4 times n minus 1, C5 times this summation, and so on and so forth until C8 times n minus 1. This is the running time of this algorithm. Clearly, this is the best we can do because we don't know the values of these TJs. So the best we can do is this. This is a function of n. But like we did in the first example, we're going to look at two different scenarios. What happens in the best case and what happens in the worst case. You know, we may be able to find the exact values of these T's or TJs, and therefore we'll be able to define our function completely in terms of n only, not in terms of n and TJs. Okay? Right, so that we do in the next slide. So the best case. The best case scenario is if you are lucky that the elements in the array are already sorted. The elements in the array are already sorted. So that if each time you take an element AI or AJ, remember we start from j equal to 2, 3, and so on. So when you pick the element number 2, it is already in its correct place. So you don't have to go inside the inner loop to be shifting it to the right. Okay? So in other words, the condition of the while loop will execute only one time. So actually j will always be 1 for j equal to 2, 3, 4, and so on. In that case, because we never have to enter the loop. So the first check that we do actually gives us false, so the loop stops. Okay, let me go back to the code just to make sure you understand what I'm saying. Okay, first time you check the loop, you find that actually AI is less than or equal to key. Okay, because remember, if j is 2, I will be 1. So AI is actually element number 1. And since the array is sorted, element number 1 is less than or equal to element number 2. It can never be greater than this key. So this condition is false. So the only check we have done is this one that gives us false, meaning this condition will be checked one time. So meaning T2 is 1, T3 is 1, T4 is 1. All of the TJs, they are 1. This will be 0 times, because if you say TJ minus 1, you are saying 1 minus 1, which will give you 0, and so on. So this is the idea. If the elements are already sorted, then all the TJs are equal to 1. And all the TJs minus 1 are equal to 0. So this summation simply becomes summation of 1 plus 1 plus 1 plus 1 and so on for j from 2 to n. Whereas this is summation of zeros, which will give us zeros. Okay, so this will help us to simplify our formula. This is what the formula will become with that assumption. Let let me again just to go back just to make sure we are clear. What is summation for j from 2 to n of 1? We are saying keep adding 1 plus 1 plus 1 plus 1. How many times? The number of times the body of the loop will execute. Because we are starting from 2, it's actually going to be n minus 1. So this is basically just saying n minus 1 times 1, which is n minus 1. But of course, because we have the C5 here, the answer is C5 times n minus 1. This is what this will become. So this term simply becomes C5 n minus 1. So this summation simply reduces to n minus 1 in that case. What about this 2? They reduces to 0, because tj minus 1, if tj is 1, will be zeros. If you add zeros, no matter how many times, you're going to get 0. So this and this are 0. Therefore, we can eliminate this term, and we can eliminate this term, and we can reduce this to simply C5 n minus 1. This is basically what we have in that expression. As you can see, we have C5 n minus 1, and the others with the summation have been eliminated. The last one is C8 times n minus 1. So our function now is completely in terms of n. And therefore, we can collect the log terms to try and simplify it. If you do that, this is what you have. The term involving n are going to be C1n, C2n, C4n, C5n, and C8n. So if you factor out the n, we will have this. The terms without n, they are all negative. So this is minus C2, minus C4, minus C5, minus C8. If you factor out the minus, then they become all positive. C2 plus C4 plus C5 plus C8. And since they are all constants, you can represent them simply as an plus b. Okay, and this is basically the idea. So what we are saying is, in case the array is already sorted, then the running time of insertion sort is actually linear in terms of n. It's an plus b. Let us see the worst case. Yeah, so here we're saying it's a linear function. The worst case scenario, on the other hand, is if you are unlucky, the elements in the array are sorted but in reverse order. So the biggest element appear first, then the next biggest element, let's say 9, 8, 7, 6, 5, like that. So the idea is, each time you pick an element, you have to shift all what is on the right in the sorted list by 1 to find the room for it. So 9 has to move here before you can put 8. When you take 7, you have to shift 9, you have to shift 8 before you can find a place for 7. Alright? So in that case, the TJs, they are going to be equal to J. The TJs are going to be equal to J. Because when J is 2, we have to shift 1 time, and then we have to do one more comparison for the to allow us to exit the loop. Okay? Yeah. When J is 3, we have to shift 2 times, and then there will be one more comparison to allow us to exit from the loop. So actually the T3 is also going to be 3. T4 is going to be 4, and so on and so forth. Okay, now notice, so for the condition or the heading of that inner loop, the TJs are all going to be equal to j. What about the body? The body of the inner loop. Okay, it's going to be j minus 1. It's going to be j minus 1. So when j is 2, the body will execute only one time. When j is 3, the body will execute 2 times, and so on. So if you go back to our original running time function, this now becomes summation of j, because tj is equal to j. So summation of j for j from 2 to n. Whereas this 2, they become summation of j minus 1 for j from 2 to n, like that. This is in the worst case scenario. Okay, so this is what I'm trying to show you, the simplification. Now, summation of j from 2 to n is actually n into n plus 1 over 2. Why? We know that summation of j from 1 to n is equal to n times n plus 1 over 2. This is one of the formulas that we proved earlier. But now we are not starting the summation from 1. We are starting from 2. So basically, instead of saying 1 plus 2 plus 3 plus 4 plus 5 and so on until n, we are now saying start from 2. Okay, the summation is from 2. And therefore, if this from 1 is this formula, this from 2 is simply the same formula but minus 1. This is why we have minus 1 here. Okay, so summation of j from 2 to n is this formula minus 1, because we started from 2, not from 1. Okay, so this is for the one of the summation. What about the other summation of j minus 1? So again, this is easy. It's simply going to be n times n minus 1 over 2. So let us understand why this is the case. Again, summation for j equal to 2 to n of j minus 1. What does it actually mean? Because you see, so let's do it. When j is 2, what is j minus 1? It's going to be 1. Plus, when j is 3, what is j minus 1? It's going to be 2. When j is 4, j minus 1 is going to be 3. So basically you have 1 plus 2 plus 3 and so on. What about when j is equal to n? J minus 1 will be n minus 1. So the last element is n minus 1. Now this is just the normal summation. The only difference is we didn't reach plus n. We stop at n minus 1. So just substitute n minus 1 in the formula and you get your answer. Remember, summation for j from 1 to n is n plus 1 over 2. But this time n is n minus 1 actually, not n. So here if you put n minus 1, and here n plus 1 minus 1 is actually n. Okay, all over 2. So this is how we get this this formula here. If we sum j minus 1 from 2 to n, this is actually what we will get. Alright, so with this 2 in mind, it means we can now simplify our running time function. It simply becomes this. So as you can see, the C5, which was associated with this, will now be just this. and the C6 will be multiplying this, and the C7 will be multiplying that. Now if you try to simplify, you will have something like this. So this time we're going to have a term with n square. Okay, there are 3 of them with n square, n times n and c5 all over 2. Okay, so you have c5 over 2 n square. Similarly here, n square times c6 over 2 will be c6 over 2 n square. And similarly here. So these are the terms with n square, and we're going to have those with n. Okay, there are many of them, and then there are those without n at all. Okay, so this is the simplification. So now we have 3 different terms actually, those with n squared, those with n, and those that are constant. Therefore what you actually have is a quadratic equation. an squared plus bn plus c, where you assume this to be a, all of this to be b, and all of this to be c, or minus c if you like, because it's a minus. Okay, so what does this tell us? It tells us therefore that the worst case of insertion sort is actually a quadratic function of m, not linear function. Best case, linear function, but the worst case will give us a quadratic function. We can also talk about average case. So average case is basically for those tj's, instead of assuming them to be j's, we can take them to be j over 2. Now if you do the simplification, you will still have a quadratic equation anyway. Okay, yeah. Now in our analysis of insertion sort, we look at both the best case and the worst case. However, for the rest of this course, we shall be concentrating mainly on worst case scenario. Why is that? There are a number of reasons. First of all, the worst case running time of an algorithm gives us an upper bound, a guarantee that the algorithm can never take a longer time than its worst case scenario. So in the worst case, this algorithm will run this much. This is usually what we are concerned about. In the worst case, what will happen to this algorithm? How will it perform? Okay. The second point is that for some algorithms, the worst case actually occurs fairly often. In other words, many times you will actually find that the algorithm will perform in its worst case. For example, searching for an element that doesn't exist in the database usually gives, you have to do it, you have to check all the elements. So the performance there will be in the worst case scenario. The best case scenario is the first element you check happen to be equal to your target. But if the element doesn't exist, you probably have to search the entire database before you can make that conclusion. So it is a common occurrence actually to reach the worst case of an algorithm. And the last point is that the average case is often roughly as bad as the worst case. So there is no point in looking for average case. Just try to see this algorithm, how will it perform in the worst case. Now the other set of points to note is that we use some simplifying abstractions to ease our analysis of the insertion sort. This is common in algorithm analysis, and we're going to use it often in this course. What are some of those simplification abstractions that we use? First of all, we ignored the actual cost of each statement by using constant CI, C1, C2, and so on, instead of looking for the actual cost. You don't have to know the actual cost. The constants are enough to give you an idea of the performance of the algorithm. Then we observe that even these constants will give more detail than we really need. So later on we have to simplify them into simpler constants A, B, C. Okay, rather than saying C1 plus C2 plus C3, we just say A. Now we're now going to make even more simplifying abstraction. And it is this. In algorithm analysis, it is actually the rate of growth or order of growth of the running time function that is important. Therefore, we're going to consider only the leading term of the running time function. For example, an squared. If the running time function turns out to be quadratic, we are only concerned with the term that has the n squared, ignoring the lower order terms because they are insignificant compared to the higher order terms. Okay. We shall also ignore the leading term's constant coefficient, since constant factors are less significant than the rate of growth. So in fact, instead of saying an squared, we will just say n squared. Okay. We conclude that insertion sort, therefore, has the worst case running time of theta of n squared. Okay. This theta actually is showing us the rate of growth of the running time function. We're going to define it more properly in the next lecture. It tells us the order of growth of the running time function. Okay, you hear people saying this algorithm is order this, order that. So this is basically what we are talking about. In the running time function, what is the term that has the highest degree? In the case of insertion, it is the n squared. So we just say the running time of insertion sort is theta of n squared. This is basically the end of this lecture. I have a few exercises for you, all of them from the book. Let's try to go through them quickly. They are from section 2.1 and section 2.2 of the book. The first one says, using figure 2.2 as a model. In figure 2.2 is that showing the steps that will be, the insertion sort will go through in each iteration to show how the elements are sorted. Okay, so using similar figure, take these random values and show how the insertion sort will work to sort these values. Second one says, rewrite the insertion sort procedure to sort into non-increasing instead of non-decreasing order. So just to modify the procedure, instead of sorting in increasing order, we now sort in decreasing order, or what is called non-increasing. Non-increasing is actually decreasing. So just do the reverse. Sort the elements in decreasing order. The third question says, consider the searching problem that has input a sequence of n numbers, a1, a2, and so on until an, and then a target value v. We want an output to be an index I, such that v is equal to the element at I. in case the element v exists in the array, or a special value nil if v does not exist in the array A. Okay, so it says write pseudocode for this linear search problem, which scans through the sequence looking for v until it finds it, in which case it will return the index, or it will return null if it doesn't. So this is the first part. The second part says using a loop invariant, prove that your algorithm is actually correct. And then finally, make sure that your loop invariant fulfills the 3 necessary properties. Yeah, so actually it's related to the second part. Improving an algorithm is correct using loop invariant. You have to show that the initialization is true, maintenance is true, and the termination is also true. So these are the exercises under section 2.1. Also under section 2.2, we have the following. Express the functions n cubed over 1000 plus 100n squared plus 100n minus 3 in terms of theta notation. What is this in terms of theta notation? Okay, so this is very trivial actually, but the second part is asking you to come up with an algorithm for selection sort. Let's go through it. It says consider sorting n numbers stored in an array A by first finding the smallest element of A and then exchanging it with element number 1. Then find the second smallest element and exchange it with the second element, and so on and so forth. Write pseudocode for this algorithm, which is known as selection sort. So this is part 1. Second part, what loop invariant does this algorithm maintain? So it's asking you to identify the loop invariant that can be used to prove the correctness of selection sort. Part 3, why does this need to run for only the first n minus 1 instead of n elements? You will see that your loop for the selection sort runs only n minus 1 times. It doesn't have to run until n. The question is why? And then finally, give the best case and the worst case running times for the selection sort. Very similar to what we did for insertion sort. You need to analyze, come up with the general running time function, and then consider the special case of the worst scenario and the best scenario. The last exercise, taking you back to the linear search. So consider the linear search again. How many elements of the input sequence need to be checked on the average? Okay, assuming that the element being searched for is equally likely to be any element in the array. How about in the worst case? What are the average case and the worst case running times? In each of these cases, justify your answer. So I leave you to think about these exercises. I may ask some of them in your first assignment. So try and do them. And as I said, our book has many other exercises, so it is always good to try and solve as many of them as you can. This brings us to the end of this lecture. Thank you very much.